Hello and welcome to the course of machine learning. Today we are going to discuss about convolutional neural network CNN. It's part of deep learning. As you know, deep learning is a subfield of machine learning concerned with algorithms inspired by the structure and function of the brain called artificial neural network. In previous session, we already discussed about neural network, how many input layer we have, how many hidden layer, and what is the output layer. And also we have the multiple layer neural network. So based on the Andrew Ng, using brain simulation, hope to make learning algorithms much better and easier to use. Make revolutionary advances in machine learning and AI. This is the speech or talk with Andrew Ng. Let's have a look to the description of deep learning. Deep learning is a subfield of machine learning concerned with algorithms inspired by the structure and function of the brain called ANN. Deep learning is large neural networks. Deep learning is a branch of machine learning based on a set of algorithms that attempt to model high-level abstraction in data by using multiple processing layers with complex structures or otherwise, composed of multiple nonlinear transformations. If you look at this picture, the question is, why deep learning? How do data science techniques scale with the amount of data? The amount of data and the performance. If you look at this picture, you will find that the older machine learnings in comparison with the deep learning, the performance of the deep learning during the amount of the data, the performance of deep learning will be increased. The x-axis shows the amount of data. The y-axis shows the performance of algorithm. You can see that by increasing the amount of data, the performance of algorithm in terms of deep learning will be increased. What is CNN? Convolution Neural Network. CNN is a powerful image processing deep learning type, often using in computer vision, that comprise an image and video recognition along with a recommender system and neural language processing (NLP). CNN uses a multi-layer system consists of input layer, output layer, and a hidden layer that comprise multiple convolutional layer, pooling layer, fully connected layer. We will discuss all layers in this lecture. Just look at this picture. In this figure, you can see that the overall view of CNN structure for image classification. The input image, like the image from this cat, are coming. They give to convolutional and non-linear. Then the next step is pooling, and the next step is flattening, and after this we have the fully connected layer. The last step is output. Let's have a look how these sections are working. So the question is, how do CNNs works? They can be used for other tasks. CNN are mostly used in tasks involving image data. Each image contains pixel data that can be represented in a numerical form. This numerical representation is what is passed to a CNN. As much as normal ANN can be used in processing image data, CNN have proven to perform better, resulting in higher accuracy. For example, an image with 3 channels is likely made of RGB. You can see this in this picture, red, green and blue pixel. So for each pixel we have 3 numeric values in the range of 0 to 255 that define its color. For an image of color depth 1, we would likely have a grayscale image with 1 value defining each pixel. Again, in the range of 0 to 255. This is the range of images. So again, I can repeat it. Each image contains pixels that can be represented in a numeric form. Here is channel, another channel, another channel. The width is 4 units pixel, high 4 units, and 3 color channel that we have. Now we have the convolution layer. This layer is the main building block of CNN, responsible for preserving the features of the picture. This layer applies some filters to the image to remove low and high level features in the image. The convolution operation results in what is known as a feature map. The feature map is obtained by applying a kernel or filter to the input images. The convolutional operation results in what is known as a feature map. The filter is usually a 3 by 3 matrix. You look at this matrix. However, other types of matrix can be used. The feature map is obtained through an element-wise multiplication of the filter with the matrix representation of the input image. The objective here is to reduce the size of image being passed to the CNN while maintaining the important feature. The filter slides step by step through each of the elements in the input images. Before I give you an example, let's have a look to this picture and see how this mathematics or numerical part happens. This is the source pixel that you can see here. From the source pixel, we have this 3 multiplied by 3 matrix. And the center element of the kernel, for example here, is placed over the source pixel. The source pixel is then replaced with a weighted sum of itself and nearby pixel. For example, here is convolution kernel emboss. Here is new pixel value and how this new pixel value happen. For example, if you look at this 4 and from that side 4 multiplied by 0 plus 0, the next cell 0 multiplied by 0 until you reach to minus 4 multiplied by 2. In some of them is minus 8. This is the new pixel value that you get as a destination pixel. After you get the new pixel value like minus 8, this is the way that the convolutional operation result in what is known as a feature map. The feature map is obtained by applying a kernel or filter to the input images. So let's have a look to one example. This is the example. For example, we have firstly the filter is positioned in the upper left corner of the image. Let's suppose we have one images, a source file. You design one filter, 3 multiplication by 3. This is your filter, the green color. Then the filter is positioned in the upper left corner. Okay, here, upper left corner of the image. Here, it indicates between the two metrics, image and filter, or multiply by each other. For example, you have in the filter you have 1 and here also you have 1. When you see 1 multiply 1, you can see. And the next is the all result should be summed. Then the result is stored in the output matrix here. See, when you have the result can be added in the output matrix. You can see in the red color. The next step is move this filter to the right by 1 pixel, also known as a step, and repeat the process. After the first line is over, the second line is passed and the transactions are repeated. The output matrix is created after all operations are finished. The reason why the output matrix is 3 multiplication by 3 is because the 3 multiply 3 filter in the 5 multiply 5 matrix move 3 times horizontally and vertically. Let's have a look to some technical parts and operation of deep learning, especially CNN. We call stride and padding. In stride, it controls how the filter convolves around the input volume. The filter convolves around the input volume by shifting 1, 2 or other unit at a time. Again, I can repeat it. Stride control how the filter convolves around the input volume. Here is an example. Let's imagine you have 7 multiply 7 input volume. 1, 2, 3, 4, 5, 6, 7 to 7 volume. A 3 multiply 3 filter, this filter, and a stride of 2. You see, this one is a stride of 2. Control the filter convolves around the input volume by a stride of 2. So, as you can see, the receptive field is shifting by 2 units. I don't know if you understand this one or not. 2 units by 2 units. Now, and the output volume shrink as well. This figure is very clear figure that you can understand what happened to this convolve by stride of 2. Normally, programmer will increase the stride if they want receptive field to overlap less and if they want a smaller spatial dimension. This is the way of the programmer. Now it's time to discuss about padding. But if you look at the previous section stride, now it's time to say in the earliest stage of CNN we need to protect as much as information as possible for other convolutional layer when applying the first filter. Here padding is used for this reason, to protect information as much as possible when applying the first filter. Here is an example of padding, and we want to discuss more about it. So now in the early layer of network we want to preserve information about the original input volume so that we can extract those low level feature. Let's say we want to apply the same convolutional layer, but we want the output volume to remain 32 multiply 3. To do this we can apply a zero padding of size 2. Remember, a zero padding of size 2. See, all 0 are available with size 2 to that layer. Zero padding pads the input volume with zeros around the border. If we think about the zero padding of 2, then this would result in 36 multiply 36 multiply 3 input volume. This is the way of padding. Another section is pooling. Pooling results in what is known as a pooled feature map, and it is also referred to as a downsampling layer. There are several types of pooling. For example, max pool, average pooling, and mean pool. For instance, in max pooling, a 2 by 2 matrix is slides over the feature map while picking the largest value in the given box. The name is obviously clear, max pooling. From here, single depth slide or a slice from that side. Which one is the maximum? 6. From another side, 8 is maximum pool. And for another side is 3, another one is last one is 4. Pooling ensures that the main feature of the image are maintained while reducing the size of image feature or further. Again, I can refer, the main responsible of pooling is to reducing the size of image but maintain the original feature or maintain the main feature. This reduces the amount of information passed to the neural network and hence helps to reduce overfitting. The next step is dropout. Dropout is a technique where randomly select neurons. You remember in neural network we talk about neurons. Randomly selected neurons are ignored during training. For example, here is a neural network. This technique dropout randomly ignore neuron or selected neurons during training. Another aspect we call flattening layer. The task of this layer is simply to prepare the data at the input of the last and most important layer. We call the fully connected layer. Generally, neural networks receive input data from a one-dimensional array. The data in this neural network is the one-dimensional array of a matrix from the convolutional and pooling layer. Here is example, pooled feature map from the previous one. You already pool, max pool or average or mean pool. Pool feature map, then this one is flattened. Means that they already did but one column of the matrix. Next step is fully connection. The fully connection, as I mentioned to you, the flattened feature map is then passed to the input layer of neural networks, because neural network is waiting to get the input, right? This time the flattened feature map is then passed to the input layer of the neural networks. The result of that is passed to a fully connected layer. After that, the result of the entire process is emitted by the output layer. An activation function is usually applied depending on the type of classification problem. For binary classification, the sigmoid activation function will be used, whereas the softmax activation function is used for multi-class problem. In general or in conclusion, full connection, it takes the data from the flattening process and perform the learning process via the neural network. Now it's time to do some practical work with CNN in Python. We understand how convolutional neural network works. We can start building them using TensorFlow. If you don't install TensorFlow on your system in previous ANN course, you can install it with this command, pipe install TensorFlow. Be careful, you have to change the environment. TensorFlow also can be installed via pipe. Run the following commands. So it's time to load or check our TensorFlow version by using this line, import TensorFlow as TF, and after you print the TF version, they show you 2.8. So next step is load dataset. Let's see what dataset we want to load. Take a look at how you can build a convolutional neural networks. TensorFlow. The CIFAR 10 dataset will be used in this research. The CIFAR 10 dataset consists of 60,000 and 32 multiply 32 color image in 10 classes with 6,000 image per class. There are 50,000 training image and 10,000 test image. Here are the class in the dataset: airplane, automobile, bird, etc., as well as 10 random image from each. You can refer to this figure and you can look at what is CIFAR 10 dataset. Again, I can repeat about the dataset. I told you we have CIFAR 10 and another new release version is CIFAR 100, or label subset of 80 million teeny images dataset. They were collected by Alex and Geoffrey. The CIFAR 10 dataset consists of 60,000 32 multiply 32 color image in 10 classes. I told you. The dataset divided into 5 training batches and 1 test batch, each with 10,000 images. The test batch contains exactly 1,000 randomly selected images from each class. The training batch contains the remaining images in random order, but some training batch may contain 1 or more images from one class than another. Between them, the training batch contains exactly 5,000 images from each class. Here are the classes in the dataset, as well as 10 random images from each. The classes are completely mutually exclusive. There are no overlap between, for example, automobile and trucks. Auto includes sedan, SUVs, things of that sort. Truck, for example, only big truck, neither include pickup trucks. In order to work on this dataset, this is the CIFAR Python version, MATLAB version, and another version. The baseline also somebody already implemented. You can follow up, and let's back to our main code and explain about this CNN project. After you load the dataset, it's time to do some splitting or pre-processing, but loading the dataset can be done directly by using cross utility. By cross utility, you can do by this one xtrain, ytrain, xtest, ytest, then from this tf cross utility dataset.cifar10, because this one is already available. The dataset already loaded. To verify the dataset can be done directly by using cross utility or looks correct. Let's plot the figure. Okay, after you load the data, it's time to plot the dataset. You can put import matplotlib.pyplot as plt. The class name is airplane, automobile, bird, cat, deer, dog, frog, horse, sheep, and truck. Now it's time to put in the figure size 10 by 10, and the range is 25. You can make some subplot and put in x ticks and y ticks and make some grids, and you can simply show it in by show. So we want to plot the first 25 images. Okay, first 25 images. When you put this one here is range 25, means that you want to plot the first 25 images from the training sets and display the class name below each other. Here is the class label, X label. I put class name y train I2 0. So here I put one loop, and now it's time to show the plot. Here is 1, 2, 3, 4, 5 to 5, and they show me the 25 first 25 images simply. So it's time to deal with the data processing or pre-processing section. So before you do or build your CNN model, you have to do some special case we call data pre-processing. The weights of a neural network are initialized to very small numbers. Therefore, scaling the images to be within the same range is important. In this case, let's scale the values to be numbered between 0 and 1. In order to do that, we just divided x train divided by 255 and x test also divided by 255. The next step is to build the CNN model. In order to build, here is where the convolution, pooling, and flattening layers will be applied. Because I show you at the beginning, in order to create the CNN model, you have to do convol, pooling, flattening, and fully connection. You have the input and output. Before fully connection, you have to do convolution, pooling, and flattening. That is why in this code, in this section, you have everything in one cell. So let's discuss what happened now. The first layer is the convolution 2-dimension layer with this command tf.cross.layer.convol2d, and you have padding, activation is ReLU, and input shape are 32, 32, and 3. So with the stride of 2. So the next step is 32 output filters with 3x3 feature map considered for the first layer. You can see that 32 by 32 output filter by 3x3 feature map considered for the first layer. The same padding, choose that the result in even padding for the input. Input shape is 32, 32, 3, since the images are of size 32 by 32. 3 notifies the networks that images are colored. If you see what is this 3, I mentioned now. The ReLU activation function, so as to achieve non-linearity, we call ReLU. The next layer is max pooling. The next layer is max pooling, that a pool size of 2 and 2 that define the size of the pooling window, and 2 strides that define the number of steps taken by the pooling window. Remember that you can design your network as you like. This is not any mandatory creation or creating or building the model. It's up to you, and it's up to your performance, how you want to apply the model. In this case, another convolution and pooling layer is created. Here is 64. The 64 output filter, read 3x3 feature map, and the same padding and ReLU activation be considered for the convolution layer. Also, the parameter of pooling layer is the same as previous pooling layer. That is followed by it's time to go for flatten. Flatten layer whose result are passed to the dense layer. The final layer has 10 units. You can see here 10 units because the dataset has 10 classes, since it's a multi-class problem. And also in this dense layer we use the softmax activation function, which is applied on this project. Model visualization. Now it's time to visualize the model. The quickest way to visualize your model is to use the model summary function. So if you want to report your model in your paper, it's fine to do model.summary parentheses. Then they will give you the model sequential model, layer, output, parameter. This is the layer in convolutional 2D, and this is the output shape, max pooling with this number, and convolution dimension 1, max pooling 2 dimension. Then this is the second layer. This is the flatten and dense 1. So total parameter is 430,000. Trainable parameter is 430,000, and non-trainable parameter is 0. Now you can simply do model summary that you can see the layer and their parameter in the system. Also in this summary you can see other parameter as well, which we discussed in previous lecture. You can use the cross plot model. You see here cross utility, there is one plot model from the cross utility. You can use the cross plot model utility to plot the model that you can see the input size and output size of each model. In order to see this one, I advise you can install PyDot using pipe install PyDot, and then install graphic viz. So the graphic viz I already discussed in previous session in neural network, and simply they can plot some interesting figure for you. So now it's time to use drop out to reduce the overfitting. One of the common way to improve the performance of deep learning model is to introduce dropout regularization. In this process, a specified percentage of connection are dropped during the training process. In this code, we consider 0.2 for dropout layer. Here is our model, cross model is based on the sequential. Okay, this is the convolutional 2 dimension and stride 2, and here between flatten and dense I put dropout. We consider 0.2 for dropout layer. So next step is to compile the model. So now it's time to compile the model. The next step is to compile the model. The sparse categorical cross entropy loss is used because the labels are not one-hot encoded. We use here Adam optimizer. In the event that you want to encode the labels, then you will have to use the categorical cross entropy loss function. What is the reason? If you want to encode the label, you use categorical cross entropy loss function that you can see in this line. Optimizer equal to Adam, loss function cross losses sparse categorical cross entropy. So for more detail, you can use the help of this function and see what will be happening. So in order to train the model, we're supposed to train the model based on 500 epoch or epoch. So because it will take a lot of time, I just reduce it to 10. Of course, the result cannot be reached to more than 60. By 10, you have to put to 500. Then you get more accurate result. Now, for me, in order to make it simple way for you, I just make it 10 epoch, and in the training the model, you have to fit the data to the training set first. Here we fit the data to training set. The validation set is passed as well. Here is supposed to have 600 epoch, and I didn't use. I just used 10, and also 600 epoch considered for the training phases. After you do or run this cell, you can see that till epoch 10 or epoch 10, you reach to this accuracy, but still the accuracy can be higher. Why? Because in 10 they reach to this accuracy. Maybe later on they will reach to higher accuracy. So next step is to evaluate the performance of model. To evaluate the performance of model, we have to do the learning curves. Learning curves are important because they can inform you whether the model is learning or overfitting. If the validation loss increases significantly or the validation accuracy reduces sharply, then your model is most likely overfitting. Since the model was saved into a history variable, you can use that to access the losses and accuracy and plot them. You can also store them in a pandas data frame that we use here. Import pandas as PD, the history, save in the panda data frame, and the loss and variable loss also available in this section. And let's have a look to this figure and how you would plot the training and validation loss. This is the validation loss, and this one also loss function. Here the blue color, and we have the validation loss. But this one, as I mentioned, depends on 10 epoch that you have. The next step is to save and load model. You might be interested in saving the model for later use. Saving the model is important so that you don't have to train the model again. This is especially critical for image models that take a long period to train. The H5 format is common format for saving cross. So here you already have the saving model. You put model.h5, and after this you can give the summary of the model. Again, all the summary of your model is available here, and also the cross load model. We set here the cross load model. Okay, load model, cross.model load model is used for loading the model again. So in order to use the calculation of accuracy, simply you can put the formula accuracy load save model.evaluate based on the test and X test and Y test data. And you can see the total accuracy based on 10 epoch is 0.69. That is why I advise you to put more training time and epoch to get the better accuracy for your research.